Welcome everyone to the last in our Eden Stories webinars. Thank you for joining us again. We think it's going to be an inspiring journey today with Paul on glaciation here. I think in 40 minutes or so trying to explain the entire landscape. So good luck with that. I think that's a big task to take on, but I'm sure Paul's up to it. My name's Chris James. I work for the Eden Rivers Trust as a communications and administration assistant on the Access to Eden project. We've organised a series of talks as part of that project, which will run for another 3 years. We're 1 year in, £2.6 million project, with £2 million coming from the lottery fund. I think just a few words about the logistics today. We'll ask Paul to do his talk. If during the talk you have any burning questions to ask, if you use the Q&A button on your Zoom screen, you'll be able to type questions in. So if we could ask you, type them in, and then we'll visit them at the end in a short Q&A session if we've got any questions to answer. But do type them as we go through the talk. If anything occurs to you, I'll invite you to ask questions at the end again, and we'll get through as many as we can. If we can't answer them, we'll go away and have a look at things and come back. So yeah, just get them typed in. And there's a CC option too for captions, if you want to use those, if you're not hearing things well or you need additional support with visual captions, then that's available too. So as for me, a couple of minutes introduction, and then we'll move on to the interesting part. I just want to say a little bit about the Access to Eden project, which is enable us to host these talks, and then we'll move right along to Paul. So the project, it's a 4-year project, as I said, 3 years to go. It's based in the Eden catchment, river catchment, funded by the National Lottery Heritage Fund, led by Eden Rivers Trust, in conjunction with a number of major partners in the area. So we've got the Cumbria Wildlife Trust, the North Pennines National Landscapes, Yorkshire Dales National Park Authority, many more besides are all joining in on this project. Its aim is to break barriers and build bridges, as it says on the slide, and I think that really says it all. We want to improve our green spaces and our blue spaces, of course, provide the opportunities, training and tools for people to actually get out, help in the landscape, enjoy the landscape. We want to train up volunteers on, surveying, water safety, plant ID. We want to know more about the catchment. We want to give visitors the confidence to explore more, and we want to improve things. And as part of that, on the map, you'll see we have 8 doorstep sites, which are going to get some extra attention from the project over the course of the project. That comes along with improved accessibility, diversity of wildlife, flora and fauna, volunteering opportunities. Yeah, so a lot of work going on at these doorstep sites as we go through the project. We've got Engine Lolling and Petrol Vale in Carlisle city centre, for instance, like prime locations in sort of big urban spaces. So we really want to encourage people to start using them and giving people better access and actually finding out a little bit more about the history of these places and actually sharing that so that these places have a bit more depth to them. And as part of that, obviously, talks like this on geology or on glaciation, actually adds to the depth of the area and then the depth of the knowledge people have. And we think will encourage people to explore more and actually find out more for themselves. As I said, submit your questions as we go through. I won't say any more on the project. I think we'll get to Paul. Use the captions if you need to. What I'll do now, I'll just introduce Paul Carling. I'm going to read his title out. He might hate me for it, I don't know. Emeritus Professor at the University of Southampton. I think we're very fortunate to have Paul today. He's going to talk for 45 minutes. I think he's well versed in talking about this subject, so I'm sure we'll be bang on. And he's going to explain the landscape of the wider region here, how it was shaped. I'm I did do a bit of reading up, I think 20 to 30,000 years ago, the last big glaciation incident, but I'm sure there have been minor ones since. So he's got a no small task really to sum that up for us. So I'm going to hand over to the expert.
Thank you very much. Well, good afternoon, everyone. When Chris James asked me to give this talk, he said, "Can you tell us something about the glaciation of the Eden Valley?" And I said no, because I'm not that averse. I'm not that converse with the detail of what happened in the Eden. I only know the generalities, but I can talk about the regional picture, not least because in recent years I completed a study on the glaciation around the upper Lune, if you like, around the T-Bay area. So I will mention the Eden as we go along, but you should be able to pick up some ideas of what kind of landforms to look for and to place the Eden Valley within a sort of regional context. So just looking at this title slide, as it states, this is a glacial erratic. And the different lithologies in the glacial sediments which have been laid down, and lithology simply means rock type, have proven invaluable to geologists working out what happened in the glaciation. So an erratic technically is one kind of rock which is sitting in a position it should not be in on another kind of rock. So here we have an example of Shap granite. This is just at Train Rigs, just to the east of Shap, and it's sitting on limestone. And people have known for a very, very long time. Local people realized that this was a bit strange, and where did this rock come from? What was it doing there? And I'll come back to erratics a bit later on. I'm going to mention the Eden to start with in a couple of slightly grainy slides, but I think it's worth going back to some earlier work just to give some context, if the slides will move. Now we're not, whoops, yes. Okay, this is a bit grainy, but you don't really need to see the detail. The Victorians got started with glaciation in the late 19th century, and Trotter summed everything up for the Eden in 1929. And one thing they realized very early on by looking at the lithologies of glacial sediments was that the actual directions of ice flow were very, very complicated. And the arrows on here represent what was understood back in 1929 as to where ice was flowing. Now, the key points here is that people often think that ice came down from Scotland progressively, sort of bulldozing the landscape and burying the landscape, but it's much more complicated than that. As you can see here, Carlisle's in here somewhere. Hawkwhistle, I think, is here. It's a bit blurry, but ice was coming in off the Irish Sea from the west, going through the Tyne Gap to the east, and there was another ice cap forming in the North Pennines. So the key point here is that you have competing ice production centres, and that was realised very early on, and they waxed and waned during the glaciation. The diagram to the right, once again, we don't have to get into the detail, but this is the Carlisle Plains, southeast of the Solway Firth. He mapped lots of different glacial deposits and mapped these lines are what he thought were different positions of the ice. As he said, during its retreat and re-advance. So the ice isn't just sort of covering the land and then melting away. It's actually waxing and waning through time repeatedly, depending on vagaries of local climate. Trotter also pointed out that the Eden and the Upper Lune was one of the most ice-congested areas in Britain, and it's still not totally understood, despite roughly 100 years of research since Trotter's time. Of particular interest to geologists has been the lowland area just south of Carlisle. And once again, these maps that we don't have to look at the detail. Carlisle's up here somewhere. And the lowland area is a massive complex of landforms that related to when the ice was retreating. There's meltwater channels, there's all kinds of complicated depositional landforms, making a complex that Trotter mapped. And even today, not so long ago, Livingston and some of his colleagues were also looking at this lowland area because it's at the interface between the ice coming down from Scotland and the ice coming out of the Lake District and the ice developing in the Pennines. So don't be interested too much in the detail here. I will come back to some of the key points latterly. Today, we would call this an ice marginal land system. And we have to remember that a lot of what we see in the landscape that we want to attribute to glaciation is actually forming as the ice is leaving the landscape, not necessarily overrunning the landscape. And we have to pick out the evidence for different stages in the development of the ice and in the retreat of the ice. So let's get some context. Why do we have glaciations? The figure on the left here, it's sort of turned around, north is to the left. And this figure shows the extent of the ice, mostly terrestrial ice, at the end of the last glaciation, what most people call the Ice Age. So I'll be talking about the Ice Age. And this, at maximum, is about 20,000 years ago, maybe a little bit earlier. But there were other glaciations before then. And in fact, if you look at the whole of the Earth's surface in the Northern Hemisphere, there are probably dozens of glaciations, although within the UK, we only have good evidence for about 3. And that's because the earlier glaciations, the evidence has been rubbed out by subsequent glaciations and other land surface processes. So without getting into too much technical detail, I want you to understand why we know that. People working in oceanography have taken cores from the deep ocean, and the deep ocean oozes far from the land where no sand and gravel is washed in, consist primarily of microorganisms called foraminifera, which float around in the ocean. They're planktonic, and when they die, they fall to the bed of the ocean. But when they're living, they grow shells around them. So these are sub-millimeter in size. And depending on the temperature of the ocean, the isotopic ratio in the shells varies. So quite simply, if it has a high oxygen 18 to oxygen 16 ratio, it means it was forming in relatively cold seas and vice versa. So we know when we have a lot of cold-based organisms, the Northern Hemisphere was unusually cold. And if we have a lot of warm organisms, warm-loving organisms, it was relatively warm. And you can see the oscillations in this ratio through time, going back to 4 million years ago in this particular record. And these oscillations have increased in amplitude as we come through to modern times. So before about 1 million years ago, you were having oscillations about every 41,000 years. And now we're having oscillations about every 100,000 years. And of course, we can ask the question, what's going to happen with anthropogenic global warming? And the reason this occurs is because the orbit of the Earth around the sun isn't fixed. It actually fluctuates a little bit. The main orbit can stretch or contract a little bit like an elastic band. So sometimes the Earth is closer to the sun than at other times. Also, the Earth in the Northern Hemisphere is tilted towards the sun, and that degree of tilt can vary, making the Northern Hemisphere cooler or warmer. And to make things even messier, we have a thing called precession, which you can call wobble. The Earth wobbles on its axis. So these 3 factors combined means that sometimes the Earth is closer to the sun than other times. And most people agree this is the cause of glaciations. So going through what happened during the last glaciation, which we call the Deventian. This is the other figure I showed you earlier, but this time rotated around, showing the maximum extent of ice in Northern Europe. And you can see that in England, the ice came down but didn't cover the Midlands and southern England and southwest England. But Wales had its own independent ice cap. And we've got a series of slides here showing how the ice built up from about 30,000 years ago and then extended and then began to retreat sometime after 20,000 years ago. So you can see at 19,000 years ago, northern England was still covered by ice. Wales had an ice cap, and sequentially, the ice retreated. There was no ice then around Liverpool, and progressively less and less ice as we come through to 15,000 years ago, when the Lake District and the Northern Pennines were completely ice-free, but there was still ice in the southern uplands and in the highlands. So the area was pretty much ice-free by 14,000 years ago. And I'll point out that the actual ice flow is complicated. It's not just a big blob of ice on the landscape. The ice is thicker in some places, and the underlying topography drives streams of ice away from what we call ice divides. So there would be little ice movement along what we call an ice divide, and there'd be strong movement away from the divide. And early in the glaciation, this Scottish ice actually amalgamated with ice coming out from Scandinavia. So what did it look like? Well, of course, we don't know, but we can sort of hypothesize by drawing analogies with glaciations in part of the world now. About 30,000 years ago, if you believe this is the Lake District, glaciers began to form that slowly increased in thickness and extended down the pre-existing valleys. So if you were there then, 30,000 years ago, you'd sort of vaguely be able to recognize the valley networks that we have today. Is that the present drainage network configuration was pretty much laid out probably more than 2 million years ago. But the ice basically followed the valleys. The ice thickened until a lot of the lower peaks were inundated by an ice sheet. So in Scotland, the Pennines, and in the Lake District, there was complete ice cover, and the ice cover fed marginal glaciers. And this is what the margin of the glaciers might have looked like towards the maximum of the last glaciation. Complete ice cover with lobes flowing off into lowland areas. And of course, it basically reverses back towards the end of the glaciation to various degrees, although there can be some re-advances, short period times, and then more rapid recession. Now, in the second slide I showed you, I talked about the complexity of the ice flows in the Eden because of interacting ice coming from the Irish Sea and ice coming off the Pennines. And here is a simple diagram that shows this very well. You had ice centers in the southern uplands with ice coming down across the Irish Sea, but you had an ice center here. I put the red box on to show the Lake District. You've got an ice center in the Lake District with ice flowing out to the north, to the south, and to the southeast. And you can see that in the north of the lakes, the ice was forced to the west and joined the Scottish ice coming down across the Irish Sea, but it also joined Scottish ice in the vicinity of Carlisle and the lower part of the Eden Valley. And the Scottish ice, effectively with the ice cap on the Pennines, blocked the Scottish ice and forced the Scottish ice away over the Tyne Gap. And the Scottish ice went all the way down the east coast of the UK, where it joined ice from the North Sea. So, you know, we had England here fighting an action against invading Scottish ice, and it was fairly successful. But you can imagine at times the Scottish ice penetrated further down, and at other times the Lake District ice may have been more successful in holding it back. And my area of interest is, if you like, the top end of the Eden and in the upper part of the Lune drainage around T Bay and eastward, and then extending down through the Lune Gorge. So there's a complex interplay here of the Scottish ice trying to get south and the Pennine ice, and also the Howgill Fells are here. They were an important area blocking the ice flow as well. But as I said, finally, the whole region was covered by ice many hundreds of meters thick. So full glaciation was between 26 and 22,000 years ago. And if you believe this picture, Carlisle's up here, and down here, the ice is retreating. The Midlands are at the bottom of the picture. Leeds is somewhere around here. And we have glaciers coming off the edge of the ice cap. And the conditions around the edge of the ice cap would have been exceedingly cold, -50, -60 in some situations. And we call this periglacial. So as well as the ice, the evidence of ice, we've also got evidence in the landscape of extreme cold freezing the soils, including permafrost, as you get now in the Arctic. So you would have had tundra grasslands or bare soils. And the ice was at least 600 meters thick over the lower part of the Eden Valley. So that's a lot of ice. Now, something that's revolutionized glacial geology in recent years is the improvement in the resolution of topography. So we now have digital elevation models, as you will know, and a lot of these now are based on LiDAR. So these LiDAR images are important because we can strip away vegetation and buildings so we can see the underlying topography much better. We can also change the lighting and the angle, and we can artificially stretch the topography we want in the vertical to see things better. And I've got an image here of the upper Eden Valley. Lazenby's here. I think this is Appleby I put on. Orton and T-Bay down here. So you got some kind of understanding of what you're looking at. You got the Lake District here with the radial lakes. Everyone talks about the radial lakes coming out of the Lake District. The Pennines are over here. But other than these big hills, if you drive up through the Eden Valley, there's lots of small hillocks in here. And these are drumlins, and I'll talk about drumlins a bit later, but they're distinctive small hillocks, and they're important for working out ice flow directions. So looking at landforms like drumlins and other landforms, glaciologists have mapped the ice flow directions at different times. So this is ice coming out of the Lake District. This is ice going to the east over the Stainmore Gap. And this is later ice flowing north down the Eden Valley towards the Solway Plain. So it's very complex. It's not a single picture. There's different pictures which are overlaid on each other. The evidence is overlaid on earlier evidence from different periods of time. The other major advance has been in the ability to model what the ice was doing. Now, we have the field evidence dating right back to the time of people like Trotter going around the landscape, recording landforms and what kind of sediments there were. And we can now run computer models based on the physics of ice flow, and we tune those models so they match the field evidence for where we think the ice was at different stages of time. And we can then use the model output and see if it fits with the field evidence. And we can then adjust the model to see if we can get a better fit with the field data, or maybe it'll show us areas where we need to go to get more field evidence to improve the model even more. And you can see even in this model, the simpler diagrams I showed earlier just shows arrows and parting lines of the ice. But the dark areas are areas of high flow rate, and the white areas are areas of very low flow rate. And you can see how complex the flow was over the UK, both in Scotland and also over in northern England. And as I said earlier, the ice sheets grew in thickness and then thinned through time. So glaciologists are interested in what areas were actually covered, when did these different events occur, what were the detailed patterns, and how thick was the ice? Uh, did it advance? Did it retreat? What kind of speeds were involved? And increasingly now, there's evidence from the marine field about how the ice coming off the land interacted with ice streams in the North Sea and around the North Atlantic margin. So we've got this pretty well constrained now. The ice built up from 31,000 years ago, decayed from 20,000 years, and mostly gone by 14,000 years ago. So 6,000 years is a very short period geologically. And another topic I can't address today is what happened to all that water? What did that water do that was melting out of this huge volume of ice? What did that do to the landscape? That's another story. So the evidence for the ice locally. Now, I think most people realize the Lake District is clearly glaciated. Well, that's because a lot of the soil mantle's been stripped away, and we can clearly see the evidence today. In the 19th century, people were still believing that the Lake District had been inundated by high sea levels, and a lot of the glacial deposits were dumped out by either high sea levels, or some people still believed in the Noachian flood. But by the end of the 19th century, most people had come round to the view that there had been glaciations in northern England and also in Wales. Now, the evidence for ice, well, this might take you back to school day geography. Cirques. At the head of valleys in the Lake District, you often have these bowl-shaped depressions. This is a beautiful one. High up in the mountains, this is bleed water in the lakes. But as you come west, there's also other cirques which are not so well developed. In the Howgills, there's one at Courtly Crag. If you like walking, you'll have seen this bowl-shaped depression in the Howgill Fells. And going down the M6 from T Bay, just as you pass T Bay, if you look to your right, there's a large bowl-shaped depression in the hillside called Great Coombe. Now, in the Lake District, although cirques is the technical name for these bowl-shaped depressions, they're locally called coves and combes. So you'll often see it on the map as something cove. U-shaped valleys, glaciers tend to carve out U-shaped valleys, and rivers tend to carve out V-shaped valleys. That's not always the case, but it's a simple identifier of a glaciation. But you may not be familiar with some of these other factors. Roches moutonnées, I'll mention in a minute. Till is the deposits coming out from under a glacial sheet, and that can pile up into large masses of material called moraines, especially along the margins of glaciers and at the ends of glaciers, which helps us work out where the ice stopped as the ice was retreating. The ice carries a lot of debris, especially near the base, and the debris can scratch the basal rock surfaces and create what we call striations, scratches on the surface. And they're important because they give us a direction of the ice movement. And erratic boulders, like the one I showed in the opening slide, train rig, are important tracers for which way the ice was moving. And then we go on, we have evidence for when the ice was retreating, things called eskers. I'll come back to that in a minute, but also lots of evidence of small rock cut drainage channels that were originally along the margins of the ice sheet and are largely dry these days. Also drumlins, I mentioned before. And of course, there's also tills and moraines associated with the ice retreating as well as with the ice advancing. Technically, we say this evidence is diachronous. That means it didn't all happen at the same time. So when you're walking across the landscape, seeing these features, they can have been formed at radically different time periods. And we have to unravel that evidence and try to date it if we can and work out what happened. And some features can overprint each other and they can partly rub out features. So even if you have a textbook which tells you what a roche moutonne should look like, the ones in the field can look a bit different to the ones in the textbook. What is a roche moutonne? They're important because they give us ice flow direction. Roche is the French for rock, and moutonne pertains to sheep. Now, when I was at school, I was told, oh, they're called roche moutonnes because these little rock masses in the landscape look like little sheep lying down in the fields. And the reason they're important is that they get smoothed on the upstream side by the ice moving over them. And there's a lot of freeze-thaw action on the downstream side. So they get plucked away by the ice and they're very ragged on the downstream side. So when the ice is gone, you end up with a smooth surface on the upflow side where the ice, where the ice was coming, and then they're plucked and broken on the downstream side. And in this case, this is near Tibet, there's clear evidence that ice was moving from the south to the north at some time. Now, why are they called moutonne? Something to do with sheep. It's not sheep lying in a field. It's because it was the French geologists at the end of the 18th century who recognized these and recognized their significance. And they used to wear wigs made out of sheep's wool, and they were called moutonne. And you see how they're rounded at one side and they have a jagged front. And that's the origin of the name, which is just a quirky thing I thought you might be interested in, the origin of roche moutonne. Tills and moraines. So till is simply the debris which is ground down by the glaciers because of the weight, the pressure of the ice flowing over the rock surfaces grinds it off. And if it gets heaped up along the edges of the glacier, it's generally called a moraine. Now, till in this region is common up to about 300 meters because most of the erosion was in the valley bottoms. And the higher areas, like on the top of the Pennines and high parts of the Lake District, the ice was very, very cold and didn't flow very freely. But in the valleys, the ice was flowing very freely indeed. And the different lithologies, the different rock types in the till, we can relate to different phases of glaciation. So at the very simplest, for example, if you go on the top of the Pennines around the Eden Valley, you'll find Lake District rocks sitting on limestone, not just the Shap granite I showed you earlier, but many different kinds of lithologies, rock types coming out of the Lake District, show strong evidence that ice was moving from the Lake District east over the Pennines. So this helps us with the direction of ice movements. Another thing in terms of age is that we don't always have an absolute date, but we can say things are relatively different in age. And one is that obviously, if you have one till type overlying another till type, the one lying on top is assumed to be younger than the one lying underneath. So this is just an example from around Bretherdale, which is just west of Tibet, that you get red tills and you get grey tills depending on their source. And that helps us work out both direction of ice and also timing. The red till is younger than the grey till. This is in Borrowdale. This is the Borrowdale that runs through the southern Shap Fells close to Tibet. if you know it from walking. And as you come up the valley from the lower car park, there's a beautiful moraine across the valley just when you get to the river bridge. There's not many moraines in this area, but that's a good example. And it helps us work out where the ice was at a certain time during the recession of a glacier that came down Borrowdale from being fed actually from ice in the Lake District and not being fed by local ice in the southern Shap Fells. Striations. I said that we have these drag marks on the surface. These are beautiful examples in Bretherdale where the ice has gouged the rock. Sorry about that. Goes the rock, either long grooves where a rock has been dragged a long way, or little nicks where a rock hasn't been in contact with the surface for very long. And in this particular example, I measured quite a lot of these, and there's three different directions because the ice was changing direction a little bit as it thinned during the retreat of the ice. There's three sets. I gave them different color codes, but basically the ice was always going down the valley towards Tibet. That's a reliable indicator. These are beautiful striations on a boulder up in Wasdale Beck, close to the A6, but they're not reliable ice flow indicators because the boulder, of course, can rotate, and it may have been in a totally different position when the striations were put on it than when it finally was dumped out as the ice retreated. Now, erratic boulders. The Victorians got very excited about erratics, and many of their walking clubs, rambling clubs, became obsessed with erratics, and they formed what they call boulder committees. And local naturalists would spend their weekends on walks recording where erratics occurred. And this became incredibly popular across northern England up until just before the First World War. Here is a Shap granite boulder sitting on limestone. And here is a Shap granite boulder sitting on sandstone. And I'll come on to this in a minute, the source of the Shap granite. And we also know that the boulders get ground down by moving, by rubbing on the base of the ice stream against the bedrock, and they get smaller and they get more rounded with distance from their outcrop. So this is an important indicator of ice flow directions. So we get indications of where the ice was going by mapping out the location of different erratics. As I said, even the people in the Middle Ages knew that they were strange because they observed the landscape because they're out there farming every day. And the local stories are that they either fell in thunderstorms or that they appeared on certain stages of the moon at night and would appear overnight. And I don't know whether they ever thought they disappeared again, but that's what they thought the origin of them was. So erratic boulders, well, there's, as I said, there's many types of erratic you can find on the Pennines, on the carbonaceous limestones of the Pennines, which are coming out of the Lake District. But the most well-known is the Shap granite because it's a very distinctive pinky color in a grey matrix and has a very small area of exposure. And the Victorians realized if they could map these, they could work out where the ice was going. And an early attempt was a guy called Goodchild, who was amazingly perceptive. And he mapped on the topography here where the outcrop of Shap granite was. And then by walking the landscape, he realized that all the Shap granite was going to the east, southeast, and to the north. There's no Shap granite going west. So he realized very early on, 1875, that ice must have been coming out of the Lake District to have spread the Shap granite across the landscape to the east. And in fact, it goes right across to the east coast, to the Humber Estuary, for example, more than 100 kilometers due east. This is the Shap Quarry, and the outcrop only extends about 3 kilometers from the quarry to the west, and the eastern edge of the outcrop is quite close to the A6 highway that runs past the outcrop. Now, what about evidence for ice retreat? Now, there's actually a lot of evidence for ice retreat on the Cumberland, on the Carlisle Plain, and I'll mention that a bit later. But one thing I did mention was eskers, which you may not be familiar with. I mentioned the ice marginal drainage channels. So you can imagine, as the ice is finally retreating, there's more melt than there is accumulation. And that melt runs off from the surface and from under the ice, and often runs along the margins of the ice and can cut channels, which are important indicators of where the ice was at certain periods of time. Now, around the Upper Lune, there's not a lot of evidence for ice retreat. But in Bretherdale, there's one of these eskers. Now, what is an esker? Well, it's a ridge of gravel. Here's the hillside. You come down the hillside over this wall, and you have to climb up again about 10 meters to get on top of this ridge. And the ridge runs away for about 1 kilometer towards the head of the valley. And looking down from the head of the valley, the esker is here somewhere. There's a deeply incised drainage channel, much, much larger than the river, the small stream today would ever cut out. And it's probably that this ice marginal channel fed the formation of the esker. And basically what you have tunnels under the ice with water coming out of them, mainly in the summer melt period, and the deposits build up to form a ridge filling up the tunnel with debris. And of course, when the ice finally melts away, you end up with a long, long ridge of debris. So that's a good indication of ice retreating. That's in Bretherdale, which is just to the east of T-Bay. Drumlins are important, and there's a lot of drumlins in the Eden Valley. Now, why are they important? This is another of these LiDAR images, but this is an image not only from the Upper Lune Valley here between T-Bay and Norton, but also the northern Lancashire Plain. And you see all these small hills, like they're half egg shaped. They're mounds of till. And you see this very well when you're driving down the M6 past Lancaster. You probably don't think much about these small, beautifully smooth shaped hills. But they're important because they're laid down by ice, and they're usually laid down when the ice is in retreat. So the ice usually isn't very thick, it's thinning, and the flow is getting sluggish. But they show the direction of ice movement. The upstream side of them are always blunt, and they have a long tapered end. And as I said, they're like, if you cut an egg long ways, they're roughly like half an egg. So they're important. I put this picture on here. This is New York State, but these are really strongly developed, and you can see here how they can stand out in the landscape, and they're much more prominent here than they are on the Lancashire Plain. But every one of these records an ice flow direction. So carrying on this theme, this is the regional picture, and all the brown marks on here are drumlins, and this is the Eden Valley. Carlisle's up here somewhere. I can't work out exactly where it is, but this is Orton, this is T-Bay. And there's two things that stand out very, very strongly. There's a strong alignment of drumlins going right across the Pennines to the east side of the Pennines towards Teesside. just north of the Stainmore Gap. So ice flow from the Lake District, augmented by flow from the Howgill Fells, augmented by flow on the Pennines, forced an ice flow over the Pennines, through Teesdale, through the Stainmore Gap, and then that ice flow amalgamated with ice coming from Scotland. And you can see the drumlins are now turning to the south, stretching out, going down the east coast of the UK. To complicate matters, there's another set here which are going to the north, up the Eden Valley. And these are overlain, in places they overlay the older set. So we know from this law of superimposition that the later set are younger, and at the end of the Ice Age, there must have been a strong flow of ice away from the Howgill Fells, up through the Eden Valley towards the Solway Firth and the Carlisle Plains. And that ice, of course, interacted with residual ice that was still trying to flow south from the southern uplands, which makes the area of the Carlisle Plain such a complicated area to work out, because you had interaction of northerly flowing ice interacting with southerly flowing ice from Galloway. So we can map this information, and we have to decide if it all applies to the same time period. So I just made a very simple map here of evidence in the southern Shap Fells over what most people call Birkbeck Common. This is Wasdale here. This is the Shap Quarry here, with the A6 is coming down here somewhere. And this is the A6 coming through here, and this is the Mint Valley. Sorry, I keep hitting the wrong button. This is the Mint Valley, and here are our drumlins in the northern Lancashire plain. So I've mapped evidence here to try to work out what the flow directions were. Coals are where ice could flow over ridges through slightly lower areas. There's ice gouged out amphitheatres, a bit like cirques, and there's 4 well-formed cirques, 2 to the west of the Lune Gorge, just south of T-Bay, and there's 2 more cirques in Borrowdale, which cuts right through the southern Shap Fells. There's a nice moraine I showed you earlier in Lower Borrowdale. There's also outwash fans where debris was washing out from the ice, making large alluvial fans. If you go there today, you don't know where all this gravel's come from. There's no source of water on these dry areas above. And there's lots of small, deeply incised outwash channels. So we can put all this information together, and it allows us to work out the directions of ice movement. Lakeland ice definitely crossed the southern Shap Fells, and local ice, both from the north, including some Scottish ice, and Lakeland ice coming from the west, amalgamated and went down the Mint Valley towards Kendal, expanding onto the North Lancashire plain. We can put this information together, and we can come up with simplified flow patterns. So here's your Lakeland ice coming from the west to the east. Here is the Borrowdale Valley. Here, T-Bay is in around about here. And Lakeland ice also just came straight off to the southeast over the Kendal area. But Shap granite was brought down from the quarry area right down past Kendal, because we can find Shap granite erratics right down on the Lancashire plains. The Howgill ice, interestingly, it just sat there like a big blob and didn't do very much during the glaciation, other than to stop the flow of ice coming from other directions. It did penetrate a bit to the west towards Kendal, but primarily it stopped Scottish ice coming south and forced that Scottish ice away to the east over the Stainmore Gap. And we can fill in a lot of detail by looking at this in more, with more time, but we don't have the time today to do so. But you understand the basic principles of how we reconstruct ice flow directions without the use of numerical models. But we can go on to use numerical models to see if the numerical models show us the same kind of behavior as we see in the field. So finally, at the end of the ice retreat, the Howgill ice retreated to the east. The ice on the southern Shap Fells around west of T-Bay and west of Orton retreated to the northwest. But then the Howgill ice, for reasons we don't know, surged northwards into the upper Eden Valley, giving us that drumlin field I showed you earlier, which is orientated northwards towards the Solway lowlands. Now, the Lune Gorge was free of ice in about 3,000 years, which is remarkably quick. And you can imagine the landscape with these retreating ice margins. And a lot of the ice on the high ground, especially over the Pennines, probably just rotted away in situ. So it would be in a very dramatic landscape of stagnating ice, slowly rotting away, with debris sloughing off the top of the ice and falling into crevasses and building up deposits. How do we get absolute dates? I talked about relative dating. If you know one deposit is on top of another, it must be younger. Well, you've all heard about radiocarbon dating, I'm sure. So that's the most common method. It's based on the rate of decrease in carbon-14, which is a radioactive element. It has a half-life, and by measuring the amount of radiocarbon-14 in something which has been alive in the past, we can back calculate when the material died, or for example, when something was buried. It's been important because it can measure from a few hundred years ago back to about 60,000 years ago. So you can see that covers the period of the last ice age, about 32,000 years ago when the ice started. But the problem, of course, is that organics are scarce in ice age cold climate because there's not much living on an ice sheet or even around the margins. So we tend to date when plants and animals actually return to the environment. So we know when sometime after the ice has retreated. So sometimes you can use radiocarbon to work out roughly when the ice had gone. So example, there's radiocarbon dates for normal remains in Kinsey Cave and Victoria Cave. That's close to Oswick in the Pennines. And it shows there are brown bears there at 14,000 years ago. Now we know from other evidence that the temperature rose at that time very, very markedly. So if there's brown bears around, the ice must have gone. So we know that the area around Oswick was clear of ice, definitely by 14.7. And 14.7 years ago, 1,000 years ago, is pretty much the end of the ice age in the whole of the region. Another method, which you may not be so familiar with, is luminescence dating. We can record when sediment was last exposed to light before it was buried. So if you have a layer of sediment put down and then it's suddenly sealed by another layer of sediment, we can work out the age when that lower layer was deposited. It works very well for windblown sand and river sands. It doesn't work well for till, but sometimes you can find water lane or windblown deposits trapped between till layers. It's also based on radioactive decay, and a natural signal of luminescence accumulates within the mineral grains, which we can measure. Now, why is this important? Well, this is important because it has a different time scale compared to radiocarbon. We can go back to 200,000 years ago with luminescence dating. And of course, because we're measuring natural sediments, we're not reliant on there being any organics. So we can go to extremely cold locations like this outwash here in Iceland, and we can measure the age of these deposits without having to have organic material. And there's an example here from Orton Crag, which is in Lancashire. there's windblown deposits were about 19,000 years ago. So we know that parts of northern Lancashire were clear of ice by 19,000 years ago, well before the end of the Ice Age, when there was probably plenty of ice still in the Lake District. Finally, cosmogenic dating. Cosmic rays alter the nuclear content of rock surfaces. Now, when ice comes down from the mountains, it grinds off the rock surfaces, it grinds away the outer part of boulders, and it basically takes away any cosmic ray legacy that occurred before the glaciation. You rub out any previous age record for those rocks or that rock surface. And when the ice retreats, the rock surface and the boulders are exposed again to cosmic rays. And we can work out how long they've been exposed to cosmic rays. And by so doing, for like this example, we could say when this was free of ice, when the ice had retreated from this position to here, making these boulders exposed. And that's very valuable because we can go back over a huge time range, 1,000 years ago, which isn't very long, that's great, and also back to 10 million years ago, but it's very expensive. Now, some examples taken from, this isn't one of the boulders, but these dates were from Shap granite boulders near Shap, gave a date of 19,000 years ago, and slightly further to the east, another date of 20,000 years ago. So when you look at the error in these measurements, there's basically the same time. So just east of Shap and probably around the Shap area itself was free of ice by 19,000 years ago. So by putting these dates on maps, we can build up lines of ice retreat through time. Has there been any more recent glaciation? And Chris mentioned this right at the very beginning. He said, oh, there was an ice age and maybe we've had other ice ages since. Well, not really. 14.7 thousand years ago, the ice was gone from the Lake District and all of northern England. But there was a short blip, if you like, climatic blip, technically called the Younger Dryas period, which only lasted 1,200 years. So after the Ice Age, things got slightly warmer, and then suddenly there was a short cold period again. And there's strong evidence that you had little glaciers in these cirques right in the center of the Lake District. And there's not really much evidence there was ever much more ice than that, or even any permanent snowfields. Although with extensive snow blowing, it would have been that permafrost environment again for 1,200 years. With strong winds blowing, you could have had permanent snowfields in some of the hollows in the region, which would have been cirques in the main glaciation, but probably only had snowfields in them in the Younger Dryas period. So that was it, the last gasp of the last ice age. So, conclusions. When you begin to look at the landforms and sediments in the round, they were not just randomly produced and they're not randomly located. By looking at the assemblages of the landforms and the different kinds of sediment deposits, we can work out how the natural landscape has formed over thousands of years. Because these different landforms and the different sediments give us information on the timing of events during the glaciation, not just what was happening in different location. So somebody once said to me in the field, oh, it's just another rock, but it was a glacial boulder. And I always like to finish with this. This is John Muir, who was influential in setting up the national parks in North America. And he wrote in one of his textbooks, I asked the boulders I met whence they came and whither they were going. He could see that there was information in the landscape about process and transport and directions of actions of ice. And I'd like to leave it there, and I'm happy to take any questions. Thank you very much.
Thank you so much, Paul. That was fascinating. I've learned a lot today, and there are a couple of questions. I'd just like to thank you for putting that presentation together and for focusing on the Eden Valley and making those changes to it. It's such a great resource for us, so that's amazing. I also, what I took from it was that really how fluid everything was and the movement and working for a Rivers Trust now, when you think of glaciation, you think of it as quite a static thing. Well, I do in my mind because of the time spans it covers. But when you hear it sort of condensed down into a 45-minute talk, you realize how dynamic the whole system is and how much movement there was in the landscape. So I thought that was fascinating. And I've probably walked high and low Borrowdale sort of 100 times now, and I've never noticed the moraine on one of those occasions. So it's fascinating to know you walk over these features and don't even know they're there. I was quite impressed that you managed to pick out eskers from the landscape. I looked at it and it didn't register anything with me, but that's probably more about me than other people. We've got a couple of questions. There's a challenging one. Well, I think it's a challenging one. It's none I'd thought up. Why should drumlins have their upper side steep, whilst Roche Mouton are the reverse with their steeper side downstream?
Yes, that's a very good
It
question,
is a good question.
and it's one I cannot answer. And the reason is that glacial geomorphologists and glacial geologists don't have answers for everything. And it seems very obvious that the upstream side should be rounded and the downstream side plucked, like with a roche moutonne. But the formation of drumlins remains a complete mystery. Many people have tried to study them, and in fact, there's some coming out from under the ice in Iceland now, rapidly becoming exposed. And people are trying to get their head around why they have their particular shape and why they form in the first place, because you get sort of basket of egg topography across the landscape. Why does the ice do that? And I'll have to just give it back to the questioner and say, well, if you can work it out, you'll be very famous.
It's a fantastic talk. I just brilliant. I think the more information people have, the more they learn when they're out. And I think it's just more encouragement to get out and see these things for yourself. I think it's really important.
Well, I like to give some clues
Yeah,
because when you walk through the landscape, and lots of people listening to this talk will like to go walking in the local landscape, and I like to try to understand what I'm actually looking at.
yeah, yeah,
And obviously, it goes beyond if you're trying to interpret what happened in the glaciation, but just recognizing why a glacial boulder is rounded I find that interesting.
yeah, yeah. It's been really. I'm going to ask you one more question because it's on one of your slides, and I like words. And you'd written that landscape is a palimpsest,
Palimpsest, yes.
and
A palimpsest, the word palimpsest comes originally from art. It means when you're painting a picture or drawing a picture, you rub something out and you overdraw it.
mm, yeah,
You either rub it out and replace it, or you overpaint or over crayon or whatever. And the landscape is like that. There are some things which stand out, and other parts of the landscape have been rubbed out and overprinted with other landforms. And some landforms can not be completely rubbed out, but they can be subdued by later processes, so they're harder to recognize. So that's why we talk about palimpsest landscapes, because they're formed over long periods of time, and they're still subject to subaerial action now. So the landscape's constantly changing.
excellent. Thank you, Paul. We'll leave it there. We'll make a recording of this talk available on the QR code we'll put up. You can get to it from there or via our website, along with all the other recordings from our Eden talks we've done over this season. And thank you for joining us. And thank you, Paul. I'll end it there.
Well,
Um,
thank you very much for inviting me.
no, I really appreciate your time. And everyone, please do share this because it's fascinating talk and we'll make that available. And
All right,
thank you.
bye for now.